Hey, welcome back, MECH1320. We're going to go through belt drives. So we're going to be going through Chapter 10 in our current textbook. All right, so we're going to talk about the different terminology, the different types of V-belts and synchronous belts, and then we'll talk about what a belt sheave is. I think this one won't be as bad for us because we've already gone through gear drives and chain drives, so understanding this isn't going to be, very difficult. A lot of the same calculations would take place, okay? But, some basic types of belts. We're going to go through all the different types of belts. I'm going to show you some pictures of belts and kind of explain to you what the different belts are used for. All right, but one of the first belts ever made was called the flat belt. All right, it was commonly used in the 19th century. Least effective, all right, because of a lot of slipping. So not very efficient. We do still use them in conveyors, but literally it's a flat belt. If we look at station 4 on the 870 trainer, all right, we have a flat belt that's sitting on there that we can take a look at. Okay, then along came the V-belt, and the V-belts work by friction. Okay, they might slip, but it sits in a groove in a sheave. All right, so that was invented in 1917, okay, by Gates. And then we have a synchronous belt. The synchronous belt has teeth. It doesn't slip, and it's the most efficient belt. And we're going to get into the details on each one of those, so I'm not going to describe them all kind of as we go there, right? So what's shown here on the side, right, those are some different types of sheaves, all right? Just how you know those relates. All right, so main advantages of belt drives, low cost, okay? We don't have to do any lubrication, okay? They actually use friction, so we kind of want friction in those cases. And they're shock resistant, okay? And V-belt drive operates on tension, so we're going to do some tension calculations when we do those, okay? And so understanding that we're using friction to pull the belt around, and we're using tension, for those calculations. So if we go through some basic terminology here, and just kind of a basic setup of a belt drive, very, very similar to what we've done with gear drives and sprockets with chain drives and that sort of thing, okay? So we have a couple different sheaves or pulleys, okay, essentially. So we have a driver, and we also have a driven sheave. And remember that those can be reversed, based on ratios or things like that, and kind of what we need. But a driver and a driven, or like I've been trying to convince you all along, it's really just an output and an input, so we kind of understand how to apply the ratio. Obviously, it's a belt drive, so we have to have some sort of belt, and we're going to get into the different belts here in a little bit. But we have the arc of contact, okay? What the arc of contact is, that's where the belt is physically touching the sheave, okay? Where it's actually sitting in the groove and being pulled around or pushing around as we kind of, want to view it. The center distance, okay, it's important that we have a good center distance so that we set the sheaves apart so that we calculate the right tension on the belt, okay? If we don't have enough tension on the belt's going to slip and fall off. Or if we have too much tension on the belt, it's going to pull and do damage on the shafts, or it's going to slide the sheath off the shaft in different scenarios like that. So, kind of two sides to it. We have the tight side, okay, that's where the majority of the tension is, okay, because that's where the driver is pulling the belt onto its arc of contact, okay, and then we have the slack side, okay. So that's the side that you're going to kind of be able to, not while it's running, but you're going to be able to kind of have more movement if you were to grab that and push that up and down. Okay, so we have a tight side, and a slack side when we do these. Okay, but if we look, this is how the operation would go, all right, in this sort of manner. So I've got some animations for you on the next slide so you can kind of understand. All right, very, very similar. So the one in the middle, though, we have a belt drive driving a gear drive. Okay, we got some planetary type gears going on in there as well. But, just a scenario how the belt drive is moving and how it's driving, and you can see where the arc of contact is, where the belt is actually touching the sheave in that scenario. Okay, so let's get through some terminology here. We want to find the effective tension. Okay, so when we do that, and we'll do some calculations at the end on a sample problem. Okay, but we're going to look at the effective tension, so TE. Okay, it's T1 minus T2. Okay, T1 minus T2. Where T1 is the tight side and T2 is the slack side. Okay. Okay, so effective tension we subtract. If we want to find the total tension, we add. We take T1 plus T2. If we want to calculate the horsepower, it's the effective tension times velocity divided by 33,000. Okay, and the pulley ratio, it's the exact same as what we did for gears and what we did for chain drives. It's the driven divided by the driver, and we're going with the sheave diameter. Okay, so the driven sheave diameter divided by the driver sheave diameter, or as we effectively know, right, output over input. So we're going to use that same ratio to do calculations. If I ask you to calculate the belt length, it's 2C plus 1.57 capital D plus little d, okay, plus the difference between the d's, d minus little d divided by 4c, okay, or sorry, d minus little d squared divided by 4c, where you're keeping track of the two different d's mainly, right? The center distance is something that you would have to measure, or I give to you, okay? Then we have to, the reason we have a capital D, right, because it's the diameter of the large sheave, and the little d represents the diameter of the small sheave when we do this, okay? So that's kind of how we calculate belt length. This equation is in your text as well. Okay, so we can take a look at how we set everything up. The equation for belt deflection, okay, is the square root of c squared minus the quantity d minus b, little d divided by 2 quantity squared, okay? So, or we can look at the span length. So, sorry, I have an error here. I've got the little t and big T. It should be big T on the equation there, okay? Or little t, sorry. Where it says span length inches, that should be little t, all right? Where c is still the center distance, and the d's are the sheave diameters, all right? So we want to calculate the deflection distance, okay? T over 64, that's deflection, and it's always in 64ths per of an inch, okay? So whenever you have the test or quiz or things like this, all right, it's always going to be in 64ths when we do this for belt deflection, okay? And deflection, you can see in the diagram here, right? That's how much that belt can, move down as it's oscillating and as the sheaves are pulling, okay? So we want to make sure, and the belt deflection is tied to the tension that we want to maintain in the belt as it pulls around, okay, and does the work. So, for an example, if we have a 32-inch, remember, quotes means inches, okay? A 32-inch span length would require a deflection of 32/64 or half an inch. Okay, so there's how you want to do that. You always put it in 64ths. Okay, so that means our belt deflection would be half an inch in this case. All right, speed and torque, we do the exact same calculations. Exact same calculations. We use our ratio. Nothing changes here. As speed goes up, torque goes down, and vice versa. As torque goes up, speed goes down. These are the same calculations we did for gears and the same calculations we did for sprockets. Nothing changes, so I'm not going to spend a lot of detail on that one. But let's start talking about what a V-belt looks like. Okay, so we can see a picture. This is a V-belt, okay, and kind of what's on the inside. Okay, and we have different sizes, different charts. So this is like a vendor data sheet. So you can go through, and it's going to give you the sizing, which we're going to go through here in a little bit. Okay, as well as giving you the top width, pitch, and I'm going to get into the details here, but you can kind of see from the diagram where the top width is, where the pitch is, where the height is, and where the angle is. So those are all important pieces for us when we start talking about a V-belt. And you can kind of see based on the shape of why it's a V-belt, where it grabs the side of the sheave and uses friction to pull it. So the sheave actually has a groove that matches the V, that matches the size of the belt. So it is important when we're sizing belts and things like that. Okay, so different types of V-belts. We're going to go through a whole bunch here, but a fractional horsepower V-belt, it's just a V-belt that's used for light-duty applications. And when we're talking light-duty applications, we're talking about any horsepower motor that's below 7.5 horsepower. Okay, classic V-belts, we use them in heavy-duty applications. We can also add notches, okay, to reduce the bending stress. And we'll go through the different types of V-belts here in a little bit. So how do we identify V-belts? They have cross-sectional areas. They're designated as the letters A, B, C, and E, sorry. And belt length measured on the circumference is designated numbers following a letter prefix. So we're going to take a look at how you can look at the V-belt, and it tells you the size of the V-belt on it. Okay? Notched V-belts are identified by an X. Okay, so that's how you'll know the difference between a regular V-belt or a notched V-belt when we take a look. Okay, so if we can, you can kind of look at this chart, but we're going to actually do a calculation here in a second. You can look at the V-belt and how it's constructed, where the rubber is, and that it has steel wire in those grooves, and then it's sealed closed. So I just have a cutaway for you of what the belt looks like on the inside, all right, and then how it creates that V. So you can look at the different layers. This is off of a Goodyear classic V-belt off their data sheet. Okay, so you can see the different structured layers that they have inside that V-belt, you know, for strength of materials and things like that. And we can look at the sizes still, right? It's A, B, C, D, E. And it tells you what all the different dimensions are that we're going to go through in a minute. But you can even look on the Goodyear piece, right? Goodyear has the A, B, C, D, E. So it's common sizes, you know, and those apply to the correct sheath size as well. All right, so let's take a look. And what do those dimensions mean? And I had it on the previous slide, so if I step back, you just can't see it well. I couldn't get a good picture for you guys on this one, but we can kind of break it down what the A, B, C, D, E size here is. Okay, so the width across the top. Okay, so we can step back, width across the top there. And it's generally flat. There's a little bit of an arc to it, but that's what we're going for. Okay, so how do we read these? So let's do an example. We have a belt that has the number A42. What's its top cross-sectional width and its inside circumference, right? Remember, circumference is the distance around a circle. So that's really, you know, how we size the belt. So the A, okay, indicates that we have a top width of 1/2 inch, and the circumference of the belt is going to be 42 inches. It's that simple, guys, when we are sizing a belt, okay? So if we take a look here, this is, you know, kind of tough to see, but if it's printed on the belt. So we have an A58, okay? And you can go back and look at the chart, but an A58 tells us that it has a width of 1/2 inch, so the belt's 1/2 inch wide, okay? And it has an inside circumference of 58 inches. It's important to know that inside circumference, all right, because that's going to be what's sitting on the outside of the sheaves. All right, so that's going to be very important, and that's where the arc of contact resides. Okay, so we'll go to the amateur trainer. Okay, we have the 950 over on the other side, and we can take a look at it, or I'll bring the belts over in class when we go through this as well. Or you're most likely watching this because you missed class or something like that, and you can look when you actually build the lab and do it as well. Okay, so if we take a look at this one, what are the dimensions of the figure below? All right, it's BX36. Remember, the X means something important. All right, the belt has a top width, since it's a B, of 21/32 of an inch, and an inside circumference of 36. And the important part is that X, it's a notched belt. So if you can look at the picture there, on the bottom part of that belt, you can see where there's notches in there so that it can have better grip. Okay, so that's very important that we understand the X and note that it's a notched V-belt. It's a V-belt just with notches so they can grip. Okay, so we have one of those by the 950 trainer as well. So you're going to go through and make sure that you identify the notched belt as well. Okay, synchronous belts, we're going to get into this in a future slide as well, so you can see some pictures, so I won't have one on this one. But it's also called a timing belt or a positive drive belt, okay, or a gear belt. All right, so you use a timing belt in this, and we're going to go through it in a little bit, and I'll show you some pictures. But when you have a timing belt, all right, there's no slip. All right, so a timing belt, you know, something in your alternator in your car uses a timing belt, so positive drive. So if jamming occurs on the V-belt will slip, but the synchronous belt will shear off. Okay, so there's kind of the difference. And you can look at it a little bit more on page 256 in your text. Okay, but let's take a look how we would size something like this as it shows up. So length, pitch, and width of this synchronous belt. Okay, so we have a 200 XL025. Notice it's a little bit different than the nomenclature we had for the other V-belts. Okay, so the length is going to be 200 tenths of an inch. okay, 200 tenths of an inch. So it's really essentially what? 200 divided by 10. So 20 inches. XL indicates a pitch of 1/5 of an inch and a width of 0.25 inches, or 1/4 inch. Okay, so kind of the difference of what we have there. Remember, there's going to be a pitch now because we have, I'm going to call it teeth or grips on this, so that's where that pitch represents there. Okay, what's the length, pitch, and width of this synchronous belt? It's 500 H150, 500 tenths of an inch. Remember, so we're going to take 500 divided by 10, and that gives us 50. The H indicates a pitch of 1/2, and a width is 1.5 inches. Okay, 1.5 inches. Now, remember, this is out of your book, so you should have your book open to that table in this piece, and use it as reference. All right, so let's get back to the timing belt that we talked about a little bit ago. Okay, or the synchronous belt means the same thing. It's also known as the V-ribbed belt. Okay, so you can see a picture of it there on the right. It has longitudinal ribs. It runs smoothly. It's for high-speed application, all right, and it's for J, L, and M. Okay, that's on 248. That's the chart we just went through in sizing those. We use these as timing belts in your vehicle and high-speed power transmissions. So you can kind of see a picture of it in your vehicle there as well. You also can use a chain drive in your vehicle as well, all right, but you can use the V-ribbed belt as well, right? There's not going to be any slipping with that. Next, we have a variable speed belt, all right, so you can see how it's got those grooves in it as far as that goes. Still being able to grip onto the sheaves, all right, so we use those in heavy power transmission where speed changes occur. All right, so we might have some variable speed stuff going on there. You can see more about that belt on page 248 and 249 in the text as well. Next, we have a banded V-belt. Okay, it's a matched set of V-belts, so they're all the same size, joined together at the top by a permanent band. So you can see the picture that I have there in the upper right-hand corner. Those are used in drives that have long center distances or drives that have high shocking loads, okay? Because obviously we're going to have more of an advantage when we have a banded V-belt, for strength, when we have that longer center distance, okay? Next, we have the narrow section V-belts. Those are also called wedge belts, okay? So the cross sections are narrower than the classic belts, and we use those for high-duty applications, so anything up to like 500 horsepower or so. Next, we have double angle V-belts. Those are used in Serpentine Drives, and they're identified by a double letter as an AA, a BB, or a CC. You can kind of see the difference in the double angle. There's an angle on top and an angle on the bottom. Now, we use them in Serpentine Drives, so you can see from the picture on the right-hand side what a Serpentine Drive is. It's where we're going to have the belt that needs to go over some of the sheaves and under some of the sheaves. So that's why it has the V on the top and the V on the bottom. So we don't have to twist the belt around. It's able to, mount on top of sheaves and underneath sheaves when we do that. So that's where those come from. All right, they're in Serpentine Drives. So that's what that means. Okay. Then we have open-ended belts. They're mainly for tension adjustment. All right, but there's a big advantage when we have an open-ended belt. We can cut the V-belt to a specific length and fit it quickly using the flexible connectors. So that's the silver piece there. So when you buy an open-ended belt, it has all those little notches in it already so that you can use these open-ended connectors to change the belt length if you need to. All right, so more adaptable. Doesn't come with like a standard, inner circumference or things like that. So we can do this. So it has a fabric blended core, all right, and that way we can easily connect like the two ends there using the flex coupling or the connector there. So it produces an endless power transmission belt, okay? Essentially, that's what that's for, all right, as long as we keep adjusting. But it's mainly used in fractional horsepower or conveyor applications, all right, or until replacement endless V-belt can be fitted, all right? So if we got something, we can adapt it until we actually get the right size we need. So just kind of a convenient tension adjuster, all right, as far as that for maintenance purposes and things like that. All right, so if we take a look at the different belt sheaves, you can see what the sheaves look like, similar to where we've got, sprockets and gear drives where we have a hub, all right, mounts onto the shaft, and you can see that the sheaves look different based on the different types of belt we have, whether we got a timing belt or double V-belt or single V-belt, different things like that. So you can look at the different pictures there and see what the different sheaves look like and how they would, be connected to the belts that we just talked about. All right. It's important to have proper sheave alignment when you do this. All right. So you can see that from the trainer down there, whether we've got, you want to make sure everything's aligned properly, and you want to make sure that you have 4 points of contact when you do these. So we can have different types of misalignment, or we can have parallel offset, so where our sheaves aren't aligned correctly. All right, so it's going to pull one of the sheaves off the other shaft. So very dangerous. Same if we have the angles wrong. All right, we're going to do some damage to the belt very quickly. Or we could have something that's angular and offset. Lots of problems there. So in your lab, make sure that you guys do this correctly. All right, we want to use a feeler gauge to check the bases for soft foot. Okay, and we've already covered that in a previous lab. All right, we want to use the level to make sure the driver and the driven shafts are level with respect to each other. Okay, so that we want to make sure that the shaft levels are relatively level to each other. And then we're going to use our straight edge in there to make sure that there's 4 points of contact, okay, on the outside hub piece of the sheave. All right, so when you put the straight edge on the driver and the driven, it should be flat all the way across the sheave. All right, on the driver and the driven. So that way we know that we are perfectly aligned. Then you're going to put the set screws on. All right, so use the straight edge to make sure everything's aligned. Then put the set screws on. We do that. You're going to do that in your lab, and it'll guide you through that again as well. Just wanted to make sure that I briefed you on that as we were going through. All right, so let's answer some questions here. What are the positive drive belts? Okay, those were the synchronous belts. What's another name for a sheave? Right, you should know that that's a pulley. And which do you think will cause a higher overhung load on the shaft, the V-belt or the timing belt, because of similar rating? So we should know in this case the V-belt, because the V-belt runs on friction. All right, so that's how it grips, and I mentioned that kind of early on. The timing belt has teeth on it, so it's not going to cause as much of an overhung load as the V-belt would, because the V-belt's using friction to pull. All right, so what's the ratio? Sorry, showed you the answer first in the animation here. But the ratio of the belt drive below, all right, if we have that, remember that's output over input. So that is driver, okay, output over input. So driven over driver when we're going through this. So in this case, if I give you the diameter of 8, all right, of the output or the driven one, and I give you 2.5 inches for the driver sheave. Okay, so it should be 8 divided by 2.5, which is 3.2. And we would use that to calculate our speed and torque. All right, so we're going to go through the exercise here, all right, just so that we know and have everything down. Okay, so we'll let all the dimensions here load so that we know. All right, so we know that we're going to be using a driver sheave that's attached to a motor here. Okay. It's 5 horsepower, running at 1790 RPM. Okay, so I just want to be able to walk through everything. The center distance is 42 inches here. So these are calculations that you're going to have to do on your quiz. All right, and I'll probably have a worksheet for you because it's an end of chapter problem. All right, so what's the belt drive? We should know that it's output over input, right, or driven over driver. So it's going to be 30 inches divided by 10 inches. So that ratio is 3. What's the speed of the driven shaft in RPM? Okay, so we're going to use the ratio just like we did with gears and sprockets. So if we know the driver is 1790 RPM and we are going to a larger sheave, right? The driven, the output sheave is larger, so we know its speed has to be less. So we're going to take the input speed, which is 1790 RPM, and divide it by 3. So 1790 divided by 3 is 597 RPM. We want to calculate the sheave velocity, right? The speed. All right, so the velocity is RPM times circumference. Remember, circumference is the distance around. Okay, and we did this when we did like in chapter 3 and went through that entire problem as well. But we're going to take RPM times circumference. So RPM times 0.262 times diameter. Remember that 0.262 is our conversion. It includes pi and converting to feet from inches, right? So we're going to take 1790 times pi times 1 over 12. That pi times 1 over 12, that's that same answer as 0.262. Then we're going to take it times our diameter. So that's 10 inches. So we end up getting 4,686 feet per second. So that's our velocity. So I will expect you to be able to do all this on the test. We want to calculate our horsepower. Okay. So horsepower is going to be our effective tension. Okay. So it's going to be 33,000 times horsepower, which is 5, divided by velocity. Okay. 32.5 pounds. So that's calculating our effective tension using the horsepower equation. So we're going to take horsepower divided by velocity, okay, and then times 33,000. So our effective tension should be 35.2. All right, and then if I ask you to find the belt length, it's going to be 2c plus 1.57 times the 2d's added together plus the difference between the 2d's squared divided by 4c. So when you substitute everything in, you should get a belt length of 149.2 inches. So those would be an example of all the different calculations that I would expect you to be able to do on a test or a quiz, and in real life, if you're building a belt drive or things like that, you need to be able to do these. Okay, so it's important that we know the center distance, the size of the sheaves, and obviously when we're using a motor, we're going to know the input horsepower and RPM. All right, guys. Well, that's everything about belt drives that you need to know, all the different aspects of a belt, how to calculate everything, what different sheaves look like as well. So next, we'll be doing the belt drive on the trainer, and you guys will actually be building a belt drive, making it run. So if you have any questions, feel free to email me. Else, guys, have a great day. I'll see you in class.